Jai Hind all of you. Today we will discuss about K-map. Myself Deepti Arora, Assistant Professor of MC Department of Karnaugh Engineering College. So in K-map, first of all, we will discuss some of the terms that need to be discussed before discussing the K-map. The first one is min term. What are min terms? Min terms are a literal in a Boolean variable. What is literal? Literal is a variable as like x, y or z. So a literal is a Boolean variable or its complement. Its complement we can say x dash, y dash or z dash. A min term of the Boolean variable x1, x2, xn is a Boolean product y1, y2, yn where yi equals to xi or yi equals to xi bar. That means a min term can be expressed as y, which is equals to x1 dot x2 plus x3, something like this. Okay. A min term has a value 1 for one and only one combination of values for its variable. That is, min term has values as 1, while the max terms, or we will discuss another terms, that will be 0. So to find a min term that equals to 1, that we can say we are having some of the variables as x1, x3 equals to 0 and x2, x4, x5 equals to 1 and equals to 0 otherwise. So what are the min terms here? That is equals to 1. So what are the min terms here? x1 bar, because x1 is 0, so its bar will be 1. So x1 bar, x2, x3 bar, x4 and x5 are all the min terms for a variable x. Now disjunctive normal forms, or we can say complete sum of products, canonical form, complete disjunctive normal form. These all are one thing only. So what are disjunctive normal form or complete disjunctive normal form or canonical forms? Here these are the sum of products. Sum of products. See here. This is the product. Dot is representing the product and this we are adding these terms. So this is the sum sign. We are adding these terms in an expression E and with the function f, which is having three variables or three literals x, y or z. So what are the terms? X, y and z. The function is f, assigning its value to E, and this is the sum of product, which is known as DNF, disjunctive normal form, or we can say canonical form. How many terms it has? For example, if we are having here three terms x, y and z, so how many total terms will be there? There will be total 2 to the power 3, that is 8 terms. How this could be possible? See, A, B, C, or you can say here this could be x, y and z. So what are the combinations here? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So these all total are 2 to the power 3, that are 8 combinations. And complete disjunctive normal form for two variable could be 0, 0, 0, 1, 1, 0, 1, 1. We can write it as x, y, x dash y, x, y dash, x dash, y dash. And in complete DNF in three variable, this is the whole term. You can count it. This one is 1, 2, 3, 4, 5, 6, 7 and 8. That is equals to 2 to the power 8 terms, and its combination is like this. So what will the function comes here? The function value will be 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. It could be any function we have applied here. So what would be the f dash? F dash will be its complement. So it would be 0 ka 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, like this. Now we have to choose for function f, that is min terms we have to choose. So what are the min terms here? 1, 1, 1, 1, 1. So we have chosen this, this. So this is the sum of product of minterms. In minterms, we choose 1 and for max term, we choose 0. Now max terms, this is opposite of minterm. Similarly, we are having literals, variables, having values, but now we have to choose 0 here. So what is ABC? Again, here are the combinations, 8 combinations of 2 to the power 3. 8 combinations are here. Now, in max term, this is the product of sum. So, plus sign is between them, product of sum. So, this is the shorthand notation of this. How we can write it with pi m, capital M represent max terms and small m with sigma m, it represents min terms, small m. So here M0, M2 and M4, M0, M2 and M4 are max terms. So it is its canonical form. Product of sum. This is sum, this is sum, this is sum, and we are having product of these sums. So it is known as max terms, or we can say POS, product of sum. So complete product of sum or conjunctive normal form. With min terms, we have studied disjunctive normal form. Now with POS, product of sum, we will study conjunctive normal form. So in conjunctive normal form, we are having again, this is a function, and what would be all the terms? These all terms will be here. So this is the function. Any function we have applied here, we have the resultant here. And f dash is the complement here. So we have to write the max terms or complete CNF. So in complete CNF, we are having these terms again 2 to the power 3 equals to 8 terms. 1, 2, 3, 4, 5, 6, 7 and 8. Again x plus y plus z, x dash plus y z, x y dash plus z, that is 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, like this. So this is POS. Now K-map, what we have to study. K-map is used to simplify these Boolean expressions. All these Boolean expressions with variable 2, variable 3, we are having a lot of variables are here. So how we can reduce this using the K-map? How we can reduce these expression? Because this expression is too large to write or too large to remember. So we can reduce this expression using the K-map. So what we have to do in K-map, it is a graphical technique, or we have to make a graph in which Boolean expression in the form of sum of product or product of sum, we have to minimize it, minimal it, sum of product or minimal product of sum. We can write it as MSP or MPS, minimal sum of product or minimal product of sum. What is the goal? Goals to achieve through K-map. There are a minimal number of product or sum terms. Each term has minimal number of literals. Literals again, variable x, y, z or a, b, c, anything. C. How we can arrange a truth table. So here we have taken two variables. First one is x, second one is y. What would be the min terms? Min terms again, sum of product. So what we are the min terms? From x and y, two variables, we are having 4 combination. Again 2 to the power 2, that is 4. So 0, 0, 0, 1, 1, 0, 1, 1. 1, 2, 3, 4. So what will be the term? In min term, we have to choose only 1. So we have considered 1 as our resultant. So we will choose 0 as a complement. So to represent it as minterm, we would write it as x dash y dash, x dash y, y here x is representing 0 and y is representing 1. X y dash, because here x is 1, y is 0, and again 1 1, that is xy. In K map, how we will represent? See, this one portion is x, this portion is y. Again for x 0 1, 2 values. Again for y 0 1, 2 values. Total 4 values. How we will represent? 0 0, 0 1, 1 0, 1 1. That is 0 0, 0 1, 1 0 and 1 1. Now see, imagine two variable sum of minterms. So this is two variable sum of minterms. This is minterm 1, this is minterm 2, and we are having sum of these minterms. So this is sum of product, that is SOP form. Now both these minterms are appeared in a row, that is this row in K map, which means they both contain the literal x dash. Both are having the literal x dash. So x dash will be here 0 1 and 0 1 here. So this is y dash, this is x dash, this is x. So this would be the term we will represent here. Now what happens if we express this or we can simplify using the Boolean algebra? See, x dash would be common, so x dash here, and y dash plus y would be common. Now y dash plus y would represent 1. From the distributed law of Boolean expression, y dash and y would be equal to 1. That is 0 plus 1 would be 1. So it is 0 plus 1, 1. What would be the remaining? That is x dash. So with K map also we are doing the same, but with Boolean expression, with Boolean algebra we have to learn its rules, and then by using those rules we can reduce the or we can simplify this expression. But with K map it would be much easier to simplify these expressions. How? See. Now another example we have taken here for this is x dash y plus xy. Now to represent it, we have made again a K map, that is again x dash, this is y dash, and here are the two terms x dash y and xy. Now what about x dash y dash, x dash y and xy? We have x dash y dash and x dash y. See, x dash y dash and x dash y in the top row corresponding to x dash. There are also x dash y and xy in the right side. Here x dash y and xy in the right side corresponding to y. This whole expression can be reduced as, see, how can this whole expression can be reduced? See, x dash and y dash plus x dash y plus xy. Now see how we will reduce. From this we are taking common as x dash, y dash plus y plus xy. So what we will get here? Y dash and y, x dash dot 1 plus xy. What we will get here? Again, x dash plus xy. We can't reduce it further now, because we can't take anything in common here. So what we will do, we can here reduce it using the K map. How we will reduce? See, from this, what is the constant value? X dash is the constant value and y dash is changing. Y dash and y is changing. So we will take here x dash. And in the next one, see, next pair, which one is the constant? X dash or y? Y is constant, x is changing, that is x dash and x. So we will take y. So this will be the reduced expression. See, here one literal is extra, here it is reduced. So using Boolean expression, we cannot reduce to its simplest form, but using the K map, we can reduce to its simplest form. That is, we have to choose what is constant in both the pairs. The constant variable would be taken, and the variable that is changing from complement to uncomplemented or uncomplement to complemented form, that would be does not be taken as a part of the Boolean expression. Okay, now 3 variable K-map. See the arrangement here. What we are doing here, in this K-map of 3 variable, we are making the columns or elements as adjacent pairs. See the writing portion. What we are doing, we are having 3 variables x, y and z. So to represent it, we are having 2 to the power 3, that are 8 terms. So we are making 8 blocks here. 1, 2, 3, 4, 5, 6, 7 and 8. How we will write it as x and yz. So x would be here. For x there would be 2 values, 0 and 1. For yz here, so there would be 4 values, 0, 0, 0, 1, 1, 1, 0, 0. See now. What would be the adjacency here? Adjacency is that each bit is changed by only 1 bit. Sorry, each term would be changed by only 1 bit, each adjacency, each term. So here it is 0, 0, that is y dash, z dash, y dash, z, yz and yz dash. See, here 0, 0 to 0, 1, only 1 bit is changing, 0 to 1. Again see here, 0, 1 to 1, 1, here 1 bit is changed, 0 to 1. Now see here, 1, 1 to 1, 0, here again 1 bit is changed. What is the purpose for making this adjacency? Whatever is the funny is that, see, why is this funny ordering we have taken? So that with this ordering, any group of 2, 4 of adjacent squares, the motive is to make the squares of minterms, that is consisting of ones only. So we can get maximum here. We have to search the square with most of the ones in it. That is, first we will search for 8, then we will search for 4, then we will search for 2. So we will make the adjacent squares on the map taking common literals that can be factored out. That is, common literals that could be factored out so that we can write it in Boolean expression. So how could we make the square? For example, this is 1, 0 and this is 0, 0. So the next term is changes 1 bit here. So this is the adjacent side. So we can make the pair like this of 4. Instead of making 2 pairs, we can make the pair of 4 with this adjacency. That's why we are taking this funny ordering. So again back to the example. So this is the ordering. These are the terms we can write again. 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. That's like. And how we can represent the terms here? M0, M1, M2, M3. Because 1, 0 is here. So minterm 2 would be here and minterm 3 would be here. Again 4, 5, 6 and then 7. Okay. Now, K-map from truth tables. How we can map K-map from truth table? It's just simple. See, this is a truth table of 3 variables, K-map, x, y, z, and this is the K-map. These are the minterms, M0, M1, M2, M3, M4, M5, M6, M7. Now, from the function, we could get that M0, M1, M2, M3, M4, M5, M6 and M7. Now we can write it here as, see, this is M0, M1, M3, M2 and here M4, M5, M7 and M6. Now write the minterms accordingly. M0, 0, M1, 1, M0, M2 कितना है 0, M3, 0, M4, 0, M5, 1, M6, 1, M7, 1. So this is how we could write the how we could fill the K-map using the truth table of minterms. Now reading the minimal sum of product from KMAP. How we read the minimal sum of product? For example, this is the KMAP and we have to find the minimal sum of product. That is, we have to find the min terms. Because we are having sum of products. With sum of product, we are having min terms and in minimal form. So this is the KMAP. We are having ones and zeros here. For min terms, we have to search for 1. So we are making the pairs now. So first pair is this, second pair is this. Now correspondingly, their variables. Here x0, the x dash, then here y and z is there. So y dash, z dash, y dash, z, y, z, y, z dash. This is x because x is present here, x dash is here. These blocks are having z and this block is having y. Here it is y dash. That's why it is written as x, y and z. Now we have to minimize it. How we can minimize it? See, x dash and x are changing. So we will cut it off because it is changing. Now which one is pair is not changing? Which one is fixed? That is y dash here and y dash here. So we have figured it out, y dash z. Now again, see this pair. Which one is changing? Z and z dash. So we have figured it out. And what is the left that is remained constant? That is xy. So in final expression, what we get? Y dash z plus xy. This is our answer. That is minimal sum of product. Now what about grouping? In grouping, again we have to make rectangles around group of 1, 2, 4 and 8 ones. Not with 1. 1 could be left as it is. So we prefer of making 8, 4, then 2 and then 1. Do not include any of the zeros. All of the ones in the map should be included in at least one rectangle. Now, what is the simplest result? For the simplest result, make as few rectangles as possible. So search first for maximum number of ones that can be paired up into a rectangle. That could be 8, 4, then 2 and then 1. Then make each rectangle as large as possible. Again, group it. Rectangles can be overlapped. Rectangles can be overlapped because if it would be a larger rectangle of 8 and then we are making a pair of 2, then it could be overlapping, could be there. For example, we have made this is our expression. So what could be the maximum number of ones can be grouped? That is 4, then again 4 and then again 4. So these rectangles can be overlapped. Now, how can we are making a map? Okay. K-map can be tricky. How it can be tricky? For example, this is our grouping. How we can make a pair? This one is the pair, this one is the pair and again this. See. This could be the pair. This could be the second pair. What about the third one? We can't make of 3. We can make of up till the 2. So it could be this or it could be this. We can't take the both. So we can take only one. Whether it could be this one or whether it could be this one. Because one could be pair up in one rectangle only, not in 2 rectangles. Okay. Now 4 variable K-map. In 4 variable K-map, we are having 4 variables. Again, 2 to the power 4, we are getting 16 min terms. Again, the rule is same. We have to make the adjacent pairs 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. See how we can put the min terms here. M0, M1, M2, M3. Because this one is M2. So 0, 1, 2, 3. Then 4, 5, 7, 6. Now from starting this, because here it is 1, 1 and here it is 1, 0. So we have to start from the bottom. 8, 9, 10, 11, 12, 13, 14, and this one is 15. This is the 4 variable K-map, and this is a representation of its min terms, that is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. This could be the representation of this. How we could solve it? M0, M2, M5, M8, M18, 13. We have to simplify this. How we can simplify this? See. This would be the K-map. These are the min terms. The blue highlighted one are the min terms that we have to simplify. That means these are containing 1 and rest are containing the 0. So these are the 1s and rest are the zeros here. So we have to make the group. How we can make the group? See. This is the first group. Now see. These are the adjacent sides of this rectangle. So we can make a pair of 4 using these adjacent sides. 1, 2, 3 and 4. From this we can make a square. Are you getting this? So what would be the resultant? See what could be the resultant. These are the min terms corresponding to this. So what would be the resultant? Here see. W dash and W is changing. What else is left? X, Y dash and Z is left. These are the constants. So we have taken X, Y dash and Z. Here W dash and W are changing. Y dash and Y. Here Y and Y. W dash and W. So what is remain here? Y dash, Y, Y dash, Y. Both are changing. So we have taken XZ and Z dash here. So our answer is X dash, Z dash and XY, Z dash. So this is how we can solve the K-map and reduce the Boolean expression into the form of minimal, SOP or minimal. So this is the final expression, how we can reduce. There would be more tricky problems. Practice all those problems and tell me whether you have able to solve this K-map or not.